Yesterday's session, we concluded by taking a quick look at what we're referring to as the classification setting over here. The difference being, when compared to previous discussions on modeling, that you're not always trying to create a regression model, which by definition predicts numerical outputs, but we are classifying, meaning the example that we'll be mentioning is, for example, defaults on the loan does not default on the loan, or else the case goes to court or the case does not go to court. You could think of lawyers wanting to create such a model as well, where given a known set of variables, will they win a specific court case or will they lose a specific court case? Now, we cannot use the MSE to rank such models for the simple fact that the MSE is based on the difference we mean subtraction, the difference squared between the model's output given a specific observation and the actual output associated with that observation. Instead, we have an indicator variable. Very often in mathematics, the indicator variable will be a bold 1, and you write like subscript. I don't have Word open, otherwise I would have shown it to you that way. But think of, actually, that example would be, it would take us, forget about any examples. Instead, the notation is uppercase I, and you're asking, is equal to or is not equal to? And what I had in mind, not that I've prepared anything, I'm trying to stick to the philosophy to maybe use a generous term of not preparing anything. But going back to the book, are we calling them labels? Let's see. Are we calling them the predicted class label? So why don't we say, for example, that we have 5 different labels. So from 1, we'll take this opportunity to perhaps revise or introduce 1 or 2 functions in Excel, which we haven't had the opportunity to discuss at this point. And let's not call them 1, 2, 3, 4, 5, because that might look numerical. So let's write label underscore, and if I use ampersand, which is that, it's going to join them. So label 1 up to label 5. And what we could do is, let's pretend that this is our data. We have this data set. So you have your variables, x1, x2, x3, x4. You have your observation, y, right? And I'm not going to fill these. But they are, or I could take a random number. Random. So imagine this is your data. Imagine this is your data, and I've pasted it numerically now. And how am I going to randomly generate? I could type them manually. By the way, that's how many observations. So let's call this observation from 1 . Let's paste it numerically. Okay, so these are our I's, right? Observation I. Shall we? So observation I. Now, I would like, I'm just creating let's not call it fake, but I'm synthetic. I'm creating synthetic data. It's not actual collected data. But let's say that, for example, this observation, you can think of these variables as whatever. Hours spent on Facebook, age, something else, and something else. So look what I could do. Look what I could do. I could randomly generate an output from 1 to 5. Just having some fun with this. Could randomly generate an output from 1 to 5. But then I could tell Excel, if it generates 4, write label 4. And there are two ways of doing it. I'm going to use an XLOOKUP. I could have probably just used ampersand immediately. I could have probably just done it like this, label like this. And those are my labels. Or else, just because I love XLOOKUP, you could tell Excel, please look up the number that you've generated in this dictionary. These are the terms I'm going to look up. And please give me, I say dictionary, it's as if going from one language to another. You could do it. And why didn't that work? Because look, I didn't use the dollar signs for the red cells, or I used them, but yes?
Before you generated a random, don't know what to call it. Yeah, thank you.
Yeah, a random value.
But what is the function, please?
I think you need to ask is, what is the random variable? What random variable is Excel using? Is it more likely to generate a 1 than a 2? Is it more likely to generate a 5 than a 3? It's a uniform distribution. So the way you would do this in R, and this gives us an excuse. I might not even be answering your question, but just bear with me. If I assume a random, a random distribution that follows a random variable. I apologize. A random variable with a uniform distribution is going to tell me how many observations would you like to, and let's say 50. And then it tells me what's the minimum value, 1. What's the maximum value, 5. Of course, what it's going to do over here is it's probably going to create numbers with not necessarily integers. So let's run it. Yes. Now what if you want just integers? I think you can use the floor function. Floor just rounds to the nearest, not to the nearest, it rounds down. And
So there's no rule.
There is no rule. What rule were you thinking of? You thinking of like an x squared rule?
Because so these are just random numbers.
Yes, I know, because unfortunately we do how many years of education till our A levels working with deterministic functions. We're used to functions that, for example, like x squared, if I give it 7, it gives me 49. If I come back tomorrow and I give it 7, it gives me 49. Yes, it gives me 49 again. No, but I will always take the coin toss as an example. That's a random variable. It's going to give you, assuming the coin, I don't know, doesn't land in the gutter or you lose it, it's going to give you a head. It's going to give you heads or tails with a 50% distribution. Over here, what it's doing is, you could take the ceiling as well. Ceiling rounds all the numbers. So let's just say this again. This generates 50. Why don't we take 100? This generates 100 numbers between 1 and 5, and each number has the same likelihood of appearing. Now, I would like, in the example in Excel, I would like to generate whole numbers. That would be a discrete distribution, and there probably is a way of doing it without using ceiling or floor. But I'm going to take the ceiling. What the ceiling function does is it rounds each number to the next whole number. So even if you get 1.1, it will round it to 2. Like this. I can save it as a vector. Let's call it just generated numbers. And if I plot a histogram, we're going to get roughly an even distribution. Yes, now I need to change the bins. Unfortunately, it's taking them between. There is a way of doing it. Breaks, maybe. Let's check breaks. Anyway, it's one of them. It's one of them. I don't quite know how to do it, but look, you have what should be a uniform distribution. So to answer your question, when Excel is told rand between, it will, each number has the same, each potential output, each potential generated value has the same likelihood. Does that help?
Yes, it does. Thank you.
Well done. Well done. Thank you. So we were saying let's use XLOOKUP. So XLOOKUP, it's going to look up over here, use the $signs to lock in the cells, which is what I didn't do for the second column. Okay, so imagine that this is your data. Imagine that this is your data, and we have how many data points? We have 17 data subjects. It could be individual. So imagine that this is our raw data. Then we use a classification model. We haven't really discussed classification models right now. Let's call it Y hat. Let's call it Y hat. And Y hat tells us, I'm going to do really the same thing like earlier. I'm just going to take them randomly. I'm going to say label ampersand. There's also the concat function, which I'll show to you. Concatenate. There are certain advantages. Concatenate, you can take over a significant array, whereas you wouldn't really use ampersand if you're concatenating more than 3 or 4 objects. Concat, label, underscore, comma, and now just the rand between 1 to 5, brackets again, paste numeric. Now you're just going to ask, are they equal? Are they equal? So we're going to look at, it's going to be the indicator function. It's going to be the indicator function. So let me just emphasize again, this is our raw data. This is our raw data. Why don't we give it a different color? So let's say green. This is our raw data. This is what we've generated. We've created the model, created the classification model. And now what we ask is, if they're equal, give a 0 to my knowledge. Let's double check. Because it's a point against you. So here, y hat I is the predicted class label. For the ith observation using f hat, that's the classification model. And I of this is an indicator variable that equals 1 if they're not equal. If they're not equal. So we need 1 if they're not equal. So what do I say? If this is equal to this, then it scores 0. Otherwise, it's an if-then statement. Score a 1. Okay, like this. And now we can calculate. We're no longer discussing mean square error, but we're discussing was it the error rate? Of course, it would be the training error rate in this case. Yeah, exactly. So they're discussing test error rate, and somewhere there is the training error rate. So what is the training error rate over here? Let's have a look. Let's have a look. We need to sum and divide by the number of observations. I'm just going to hard code it, and it's 17. And that's probably considered a really bad error rate in most situations. You got most of them wrong. Not the best model. Of course, this is all for demonstration purposes. Okay. As always, what we really want is the test error rate and the test mean square error. A good classifier is one for which the test error is smallest. The Bayes classifier. Bayes is an individual. I'm not entirely sure which century. Let's have a look. It is possible to show, though the proof is outside the scope of this book, that the test error rate given in 2.9 is minimized on average. I guess on average, just the expectation, just like over a number of models by a very, actually that's wrong. Well, not over a number of models. So you have your model and you give it one set of test data, then you give it another set of test data, and then another set of test data. So you have your model, and you calculate the test error rate. You calculate the test error rate. So one model, imagine you have your f hat, and for that f hat, you can calculate the test rate for one batch of test data. Let me just widen these. So you have test data batch number 1. So batch 1 of test data, and gives you, I don't know, a 56% test error rate for this f hat. Then you test f hat again for a second batch of test data, and it gives you a 30%. There are going to be differences, right? It's different test data. Although usually you wouldn't expect major differences, whatever I mean by major. So you can minimize, so this is a theoretical result. You can minimize the test error rate on average. And by that average, we simply mean the average. For example, you have 10 batches of test data sets. For a specific model, and you're testing that model, you're ranking it. You'd like to calculate the error rate, which is similar to the mean square error that we've been discussing these past. Feels like longer, but I think it's been like 2 or 3 sessions since we first introduced the mean square error. And then you can calculate the mean of each test error rate. And what we're reading over here is you can reduce the test error rate on average, you can minimize it by a very simple classifier. that assigns each observation. So this is a model. This is a model over here. How is the model, and we're describing it as a very simple model. How is the model going to classify? In the following way: it shall assign each observation. So it shall assign to each of these green observations to the most likely class given its predictor values. So as soon as we mention likely, that's a probabilistic measure, right? So we're speaking of probabilities. Just get my phone so we won't lose track of time. Given its predictor values. In other words, we should simply assign a test observation with predictor x naught to the class J, for which the probability that y is j, given the input variables, is largest. So there's a lot to unpack over here. And in fact, when you see that vertical line, it's called a conditional probability, which is why I read it as given that. It is the probability that y is the variable that you're trying to predict. So imagine favorite movie, since we're classifying. You have 50 people in front of you, you need to guess their favorite movie. It's qualitative. It is a probability. It is the probability. We normally drop the R, but this book seems to be using PR for probability. That your variable, the variable that you're trying to predict is J, given what you know about the observation, that's X naught, given what you know, remember, this isn't like secondary school statistics. Secondary school statistics, you're just given data, I don't know, heights of individuals, and you just summarize it. In statistical learning, you're trying to relate the heights of the individuals to their diet, to their parents' heights, to whether they had any major sicknesses during their infancy. This very simple classification is called the Bayes classifier. In a two-class problem, so two-class is just binary, where there are only two possible response values, say class 1 or class 2. Imagine dies, does not die, for instance. Take maybe a bit of a morbid example. Think of the most recent pandemic. Given that someone gets COVID, in 3 weeks' time, is this person dead or alive? Well, you're not just going to, you need to look at their underlying, and in fact, the chat is asking, would that be binomial? Binomial probably plays a part. Whenever you have either something happens or it doesn't, you will find usually somewhere the binomial distribution lurking. There are only two possible response values, say class 1 or class 2. The Bayes classifier corresponds. Oh, right. Okay. So you want the largest probability. Well, if there are only two possible classes, which is why I think we're using two colors, but now we'll see. Then it is class 1. The model will say, this observation that we had in green, this observation is class 1, I don't know, dies. If this whole probability is greater than 0.5, there are only two probabilities. Either y is 0 or y is 1. So if you want the largest, well, clearly it's the one that's greater than 0.5. And class 2 otherwise. Yes, there is the edge case, I guess. What if it's exactly equal to 0.5? I guess those are material. Figure 2.13 provides an example using a simulated data set. Again, whenever you see the word simulated, it's when I describe the authors playing God. So they know the relationship in advance. And with maybe an error term, they say, okay, let's create 100 observations. It's similar to what we did yesterday. We said we know the relationship. We took a quadratic relationship. We said we also know the error term, and we generated, I think it was 100. I think it was 100 simulated observations. The orange and blue circles correspond to training observations that belong to two different classes. Right, so what's going on over here? What's going on? I would compare this if I've understood. And for the sake of transparency, I have next to no experience using classification models. I would compare this intuitively to this diagram, to a diagram like this, where you have two input variables, x1 and x2. They happen to be years of education and seniority over here. In a regression model, you have like this third axis. You have this quantitative output, or this numeric output is what I should say. Whereas over here, it's practically the same thing, with the exception that it's just a color. It's orange. You don't have, I mean, in many ways you do, but you don't have a third axis, or that third axis is, you're either on the orange level or you're on the blue level. But there's no natural way of ordering. Should I write orange above the blue? Should I write it the other way around? So instead it looks flat. But I still would encourage you to think of it as a three-dimensional diagram. You have two dimensions which are quantitative, your x1 dimension, your x2 dimension. Those take the place of these four observations. Do you have a question? Yes.
Can you show the diagram again?
Of course.
The circles, they're not the raw data, right?
This is our raw data. Yeah. This is each observation. So what are we saying? We are saying let's pick an observation at random. Let's say this one. What we're saying is it has an x1 value of so much. It has an x2 value of so much, and it has a y value, orange. So those are your three dimensions. Imagine you have 10, 57, comma orange. What the model is doing is, if I tell it X comma 57, and I don't give it the orange or blue. Remember, orange and blue, just think of it as dies, does not die, gets fired, does not get fired, gets promoted, does not get promoted, goes to court, does not go to court. Something binary for the sake of simplicity. If I only tell the model x1 is 10 and x2 is 57, does it correctly predict whether it should classify this observation as orange or blue? I don't know if that works.
I mean, you know the answer, but the fact that I know that the circles are the raw data, that's a bonus for me.
The raw data. So this is the training data, but then you use it to make actual predictions on test data. Test data, you won't know the output. The raw data is what I had over here. Now over here, I guess this is a bit more complicated, but it's the same principles. So the raw data is 16, 10, 15, 10, label 2. Then the next data point, 15, 13, 10, 12, label 1. Now what the model is doing is, if it only has this data, is it able to correctly predict the Y variable, the output? If the model knows that I spend 10 hours a week jogging, 12 hours a week with my children, 9 hours a week reading online newspapers, and 14 hours a week watching the news, how likely am I to vote for political party number 1, political party number 2, number 3, number 4, number 5?
Mm-hmm. Yes.
Okay.
And you mentioned the third dimension. I'm not saying the third dimension.
The third dimension is, one second. So if I had to ignore these, let's take the raw data. The raw data is this. Let's even remove the name of the observation. Give me a sec. Let me also copy a question from the chat. I'll put it here, otherwise I'll forget. Can't I? Where did I paste that? Here we go. Listen, look. Where were we? The diagram in the book is assuming that we know 2 pieces of information about every data subject and would like to predict either, imagine only 2 political parties. I don't think it's too hard to imagine that in our specific case. Party number 1, party number 2, the orange party and the blue party. So if the model only knows how many hours reading the specific newspaper and how many hours a week on Facebook, can the model, with those 2 pieces of information, correctly predict which party such an individual is going to vote for if an election had to take place within the next 24 hours? Those are 3 dimensions, 2 quantitative variables, x1 and x2, and a third variable, which is qualitative, political party number 1. Let me not even say number 1, just in case I give the wrong idea. Political party blue, political party orange. What do you think?
Yes, it helps.
It should help. These should be quite intuitive ideas. I'm not saying that to discourage you. There will come a time where it will just click. Now, another question in the chat was, so this is a bit of rolling regression. in the sense that we have a model and we're testing its predictive forecasting powers and then calculating how far off it was from the actual. Should I say yes? I think in spirit, yes. Now, if I had to look at each specific word that you've used, we're not updating by rolling regression. I kind of understand that you're updating the model. And maybe, yes, you could use this to update the model. We're testing its predictive forecasting power. Yes, right? We're testing how good. We are quantifying how good. That's in this over here. It's a classification model, so we're not calculating the mean square error. We're instead calculating the test error rate or the training error rate. So yes, please.
So the purple part, that's the decision boundary, right?
Well done. Well done. Yes. Yes. In this case, it's the Bayes decision boundary. There might be different boundaries. So what the model is doing is the model is trying to, I guess segregate would be one word, one way of putting it, minus the historical connotations. It's trying to segregate. It's trying to see, how can I create two buckets based on X1 and X2, so that if the X1 is less, if the X1 and X2 gives you a point which is in this blue region, then it's going to automatically classify it as a blue. The prediction would give blue. And again, orange and blue, just think of simple examples. Dies does not dies. If you're a life actuary, that's the one question you're typically asking yourself.
So it's almost a cutoff point, the purple.
I would agree, and that cutoff would be based on this probability. If it's greater than 0.5, then you will assign to this observation X0 1. So one could be orange for all I care, etc., etc.
And sorry, and with regards to Bayes' theorem,
yes, of swapping the order in the conditional probability.
Yeah, I was going to ask, but this is more of a finance question, to be honest, not actually.
Ask.
Because because human beings, we tend to, I mean, statistically, okay, there is this Bayesian theorem, and we are supposed to stick to Bayesian fundamentals.
I think that's how humans operate. Yes.
Yes, but for instance, in behavioral science, it was observed that as a matter of fact, people do not actually act rational, and by extension, they deviate away from this Bayesian fundamental.
Well, definitely. I think you can manipulate humans. Think of the lottery, for example. If the prize is large enough, well, you can forget your Bayes principle. Your Bayesian principles. Agreed. But that might be for another session.
Yes.
Okay, but thank you. Please keep them coming. Anyone else at this point? Figure 2.1, well, 13, right? It's the 13th one. Provides an example using a simulated data set in a two-dimensional space consisting of predictors. That's what you know. If I know X1 and X2, I need my model to predict, is it orange or is it blue? The orange and blue circles correspond to training observations that are going to be used to fit the model, train the model, that belong to two different classes. For each value of X1 and X2, there is a different probability of the response being orange or blue. Since this is a simulated data set, we know how the data were generated, and we can calculate the conditional probabilities for each value x1 and x2. The orange shaded region reflects the set of points for which probability y equals orange given x, it's simulated, so the authors can do this, is greater than 50%. So the assumptions that the authors have used, the relationship that they have assumed, that they've created some kind of relationship. We don't know it. It's just a diagram over here. It will give orange. It will give orange where the probability is greater than 0.5, that you get orange. Don't worry about this. Don't worry about this. The most important thing is that we read through it. The purple dashed line represents the points where the probability is exactly 50%. This is called the Bayes decision boundary. The Bayes classifier's prediction is determined by the Bayes decision boundary. And I'm already lost in these sentences. The observation that falls on the orange side of the boundary will be assigned to the orange class, etc., etc. The Bayes classifier produces the lowest possible test error rate, called the Bayes error rate. So the Bayes classifier, this goes back to what we said earlier. If you use this to classify, if you use this kind of probability, you will get the minimum error rate. You get the minimum test error rate, I think. And this is the formula. So we're taking, I'm going to skip it. Don't worry. I'm going to skip it. And I'm actually going to just skip to this now. K nearest neighbors. In theory, we would also like to predict qualitative responses using the Bayes classifier. But for real data, we do not know the conditional distribution of y given x. And so computing the Bayes classifier is impossible. Therefore, the Bayes classifier serves as an unattainable gold standard against which to compare other methods. Many approaches attempt to estimate the conditional distribution of y given x, and then classify a given observation to the class with highest estimated probability. So if we back up, all we're describing over here, or all we're describing here, is that if you've simulated your data, then based on that simulation, you can actually calculate these probabilities based on the way you created the data. So remember, for example, yesterday we created the data, we assumed the quadratic relationship. The authors are doing something similar over here, and they've created this data set. They've used some kind of formula. Now, usually you won't be able to predict the exact probability, but you can calculate an estimated probability. One such method is the K nearest neighbors classifier. Given a positive integer k and a test observation x0, the K nearest neighbors classifier first identifies the k points in the training data that are closest to x0, represented by n0. Let's find the diagram. So let's take this diagram. And you have a specific observation. Remember, x1 against x2. So you would like to say if I have an observation with these two characteristics, this x1 and this x2, is it going to be blue or is it going to be orange? Okay, very simple, very simple. We don't know yet, so we've just kept it, we've just drawn a cross. Now what you will do in K nearest is, let's say K is 3. Let's say K is 3. And you're going to start working your way outwards until your radius, the circle's radius, is long enough to capture 3 observations. K nearest neighbors, 3 neighbors. And those are, in this case, orange, blue, and blue. So I would imagine, although I have absolutely no experience, and it's the first time I'm even reading about such things. I've heard about it, but that's it. I would imagine, based on K equals 3, you're going to assign a blue to this data point, for the simple fact that there are more blue than orange. Let's see. Let's see. By the way, this might be a good study technique for any subject, really. Always try and anticipate which direction or the next step that your slide pack is going to take, a book such as this case, because if you correctly anticipate, that means you're on the right track. If you get it wrong, then clearly maybe there's a flaw in your overall understanding. I find that a really great way with really anything, right? Not just studying, by the way. It then estimates the conditional probability for class J. Class J is either orange or blue, as the fraction of points in N naught. N naught is the neighborhood whose response values equal J. Okay, so you're going to calculate 2 probabilities. Why 2? Well, because it's 2 classes in these simple examples. You're going to calculate the probability that this is blue, and you're also going to calculate the probability that this is orange, based on the J. J is qualitative data. Y is the variable that you're trying to predict. For example, voter intention is someone intending to vote orange party or blue party. J is the actual party, one of the possible parties. It can't be the red party if there's no such thing as a red party. That probability is just 0. And this, I think it's a really great idea if we put everything in the same place. This, and let's take this as well. Second. Okay, hopefully I'm still sharing Excel. If I'm not, do let me know. So let's see. So you know your test data's variables, with the exception of the output. The output is what we're predicting. And don't worry if it's a lot to take in. Don't think I'm understanding it 100%. We'll get there. So x equals x naught is, this and this. I'm using the same colors, okay? Now, let's see. Let's see. You're going to take the neighborhood. I'll use blue because they seem to be using blue over here. I'm going to take the neighborhood. Let's shade it. This neighborhood. And we have an indicator variable. So what are we going to ask? We're going to ask, now how are we indexing? How are we indexing? What does this I represent this time round? Please watch out for the I. The I means all the I's in the neighborhood. So it is this, this, and this. Let's say they were observation 50, observation 55, and observation 70. So we're going to calculate this for Y50, Y55, and Y70. And it's going to give a 1 or a 0. A 1 or a 0. Well, let's see. Let's say we did it for the orange. Let's say we did it for the orange. Like I said, the ideas are quite intuitive, but you are expected to struggle with them. And then suddenly everything will click. So if I want orange, I don't know, do we have a volunteer? Can one of you give me the probability, the estimated probability? If I told you, can one of you give me this value? If I ask probability orange, given the two pink input variables, the two pink known variables. But the diagram isn't very clear, is it?
Is it 1/3?
It's 1/3, isn't it? It's 1/3. Because hopefully, although I probably should have zoomed a bit more, it's just this orange one out of 3. So it's this really complicated looking formula, but it's something you could show to anyone still in primary school. It's 1/3 for the simple fact that we're taking k equals 3. You look at the neighborhood, you look at the smallest neighborhood that contains 3, centered at the observation point. So it's a really cool idea, isn't it? So this is how to estimate probabilities. This is how to estimate probabilities. Obviously, probability blue is going to be 2/3 now. And those probabilities should really hopefully add up to 1 if you've exhausted all the different outputs. Okay. Let's go back to the book. Very often these formulae, I don't know about you, but when I see a formula, I think it's quite a natural reaction. It can be a bit intimidating the first time. And I realize maybe the notation isn't, so we all know what summation notation means. We're adding just zeros and ones. They could all be 0, they could all be 1, or some kind of, yes,
the
please.
I is the index, right?
The I.
No,
The I is the indicator variable. When you have I in this book, it means its output, that's a function. It's a function that gives you either 0 or 1. It gives you 1 if the color of the observation is equal to the J color. So if I'm speaking about orange, if I want to know what's the probability that I get orange, then it will say it will give a 1 to those observations that have a color orange.
thank you.
So what if we took, for example,
Sorry, just one question.
Mm-hmm.
The k equals 3. In the
Mm-hmm.
diagram, that's illustrated as the size of the green circle.
Yes, so let's say it was, for example, k is 5. So k is 5. K is 5 is, and I start going out, 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 out until my circle has captured. It needs to be always centered at the observation that you're interested in.
Understood. Yeah.
So over here, this is K5, and you would get a probability of orange 3 on 5 and the probability of blue 2 on 5.
Understood. Thank you.
Okay, very good. Thank you. Excellent. Let's remove all this. Finally, KNN applies Bayes' rule and classifies the test observation X0 to the class with the largest probability. I don't want to get lost in the details, but the idea is that, for example, this one, it's the same diagram. It's the same diagram, but this is pre-application of the model, and this is post-application. So I'll do red. This is before we've applied any model. Green is the model. Green. Now this is the model. We're making predictions. We're saying, I wonder if I can translate everything. Let's go from here. Let's go from here. Let's find it. So it's roughly here and here. So the prediction that we're making about this observation is that it would be blue. If there is such an observation, if there is someone with this X1 variable and Y variable, so many hours of Facebook and so many hours watching television, then we classify them as blue. Now, it might be true, it might be false, but the model is going to perform that classification. I think we can safely skip, although it does get a bit more interesting now, doesn't it? So as K grows, the method becomes less flexible and produces a decision boundary that is close to linear. Interesting. This corresponds to a low variance but high bias classifier. On the simulated dataset, neither K equals 1 nor K equals 100 give good predictions. They have test error rates of around 17% and 19%. Okay. The black curve indicates the KNN when K is 10, the black curve. Oh, interesting. Oh, very good, very good. So this is the real decision, but this is the decision boundary if you're sort of playing God. And this is what we've managed to approximate using KNN. They're pretty close, aren't they? So it's doing a good job, so to speak. But then you have K1. So this is kind of like overfitting. It's really, really close to the decision boundary. And K100 is the other extreme. So notice the parallels between regression and classification. Regression is when you're predicting a quantitative variable, so lifespan. How long is someone expected to live if you know how many, I don't know, their diet, their smokers, non-smoker, etc., etc. This is a classification problem, and we have the same kind of ideas in classification that we discussed when we were doing regression. Variance, bias, linearity, overfitting, flexibility. And this is the error rate. This is the error rate. And again, you're trying to reduce the error rate. So so forget about the training. You want to reduce the test error, and you test you reduce the test error. This was the lowest test error rate of whatever of, so it's only getting like 13% of the prediction is wrong. Pretty cool, right? This specific model, if each point is a different model, let's make this clear. It's similar to these diagrams where we had 3 different models: the orange model, which was linear, the blue model, which was something else, and the green, which we were describing as overfitted, which we were describing as maybe placing an over-reliance on the specific training data, finding patterns that aren't in fact present in the general population. Remember, you're always looking at a sample. If you're looking at Facebook accounts, even if you have every single Facebook account, you don't have the information of a Facebook account that's going to be created tomorrow. So that might not necessarily follow the same patterns as the data that you've used to design your model. So it's the same ideas, The only difference is that they've created many, many more models. Each point is a model. So forget about 3 different models now over here. I don't know, it could be maybe 20 models. And how are they creating all these different models? Each one is a K nearest neighbor model, but based on a different K. It's based on a different K. So for example, let's take when K is 10. When K is 10, don't ask me why they're plotting 1 on K. It must be to get some kind of, looks a bit like kind of like a linear relationship. When K is 10, the prediction error is of, well, that looks maybe like 13%. So when K is 10, right? Because 1 on K is 10%. So K would be, does it work like that? Do I do reciprocal? So instead of 10 on 100, it's 100 on 10. And that's exactly what they took over here. So apparently over here, what they're saying is that once they got a fresh batch of data and they use it as the test data, the model performed, quite well. And well, next to these other models, it definitely performed pretty well, because out of every 100 predictions, it's getting less than 15 of them wrong, which I don't know, that may very often be pretty good. So the KNN training error rate, which is blue, 200 observations. I don't know what that means. And test error rate, 500 observations. All right. So they use a training, and we'll wrap up. I realize it's time. They use 200 observations to train the model. I'm using singular. That's incorrect. I should say models for every K, and K determines, K is a good proxy. Just think of K as the size of this disk. So 200 observations to train each model and test. And now they use 5,000 test observations to judge the model. Excellent. And tomorrow we can maybe take a break from all this theory and look at, I would imagine probably this chapter just introduces the basic functions in R that we're going to, for example, look, we read a CSV file. Probably we'll be writing a CSV file as well somewhere. So let's stop over here.